right, we are going to discuss the idea of efficiency of a simple machine, and this is a relatively easy thing to describe. Efficiency of simple machines. Now, what does efficiency mean? Well, let's just kind of think out loud for a minute. Um, Efficiency describes sort of a comparison. Efficiency is a comparison of what you get out of something, the output of something, compared to what you have to put in to get it, right? So it's kind of like how much work do you have to put in on the bottom of this comparison? Remember in math, a fraction is a comparison. And so when we write a fraction in math, we're basically saying the output compared to the input. So the input is how much work you have to do to get something to happen. And then the output is what actually happens. So when you think about simple machines, they all ideally should be the same on the top and the bottom, which makes the fraction 100%. But that's not the case because we have losses. There are always losses in simple machines. And these losses are because of things like friction and rubbing against things, surfaces touching each other. And we know, we've seen that when you push up a ramp, for instance, you have to push a little harder to combat the friction. You have to beat the friction on the ramp, which you don't have to do when you're lifting it straight up through the air so much. So the friction is an extra problem. It's a loss. We have to do a little more effort there. You can also have things like with a lever, for instance, if you have a nice board and you're trying to lift something, well, in a perfect world, the board would stay rigid and straight. But in reality, we know that the board can bend or flex a little bit. And this flexing, this stress and this strain that's put on the lever itself can rob you of some of your mechanical advantage, right? So these losses are occurring, which means that when we look at reality, the top of my fraction, the output, will always be less than the input. You're never going to get exactly what you put in. You're always going to have to work a little wee bit harder to compensate for the friction. But remember, working a little bit harder is still an advantage because the whole point of machines is we do a little bit of extra work because we have to go through a greater distance, but we can do it with less force. That was the whole trade-off. So we walk a little further, but we push less hard, you see? And that worked out to be sort of the same thing. In fact, next unit, we're going to talk about the concept of work and what that means in physics and how it does rely on both the force and the distance. But we haven't got that far yet. So for now, we're just using this term loosely to describe how much we're doing, right? And how far we're going, how much force we're pushing and how far we're pushing it. So let me just erase some of these scribbles that I put here. And let's go back now and let's look at this expression, this fraction that I've written a little more closely. So let's think about what it would mean. The output is basically what we get out of a machine. And so that's basically what's happening to the load. So if we think about it, the load, there's a force on the load, right? And there's a distance that the load is moving. Multiplied together, those two things represent the output. And then the input is us doing the pushing. So that's our effort force. And how far we have to push to do it is the effort distance. So this comparison turns out to this. It's comparing what's happening with the load on top, the force and the distance it moves, and what's happening with our effort, how hard we have to push and how far we have to actually move. And so that is now what the efficiency would be. Now, I'll just jump over here. I'll put a little line down the middle, and we'll jump over to the other side here. Just kind of wiggle up here. So then my efficiency is, what are these things equal? Well, what that is it's actually this. It's actually FL. I could break that apart into two fractions, can't I? Times DL and DE, the effort distance, effort load. That is the same thing as what I've written over here, just kind of pulled apart as a multiplication. So I didn't change anything. And now we should recognize something. We should notice. Remember from way back, a couple of videos ago, AMA, the actual mechanical advantage, was described as the load force compared to the effort force. It was the ratio of forces. That's what I have here. So my first thing I have here is actually just the AMA. That's what FL over FE is. Now there's something weird about this next part here. If I jump down here, remember IMA is the distance effort compared to the distance load. It's sort of like the upside down of what I have on the right-hand side here in my expression. It's not quite right. I can't write IMA there, but here's what I can do. I can take the reciprocal of the IMA and the reciprocal of the other side. When we take the reciprocal of a fraction, we sort of flip it upside down. So what I have, this thing here, which is the same as this here, is actually 1 over, or the reciprocal of IMA. It's not the IMA, it's the upside down version of it. And now when I multiply these two things together, it looks like the efficiency is going to be the AMA divided by the IMA. And these are easy numbers that I can get. I can figure out the AMA because we've learned how, and I can figure out the IMA because we've learned how to do that. And so then I can just take my answers and throw them in this little convenient fraction, and that will tell me the efficiency. Now, when you do this fraction, you're going to get a decimal because the top is always bigger than the bottom. Sorry, the top is always smaller than the bottom. We said that. The actual mechanical advantage is always smaller. And so what we do is, instead of using it in the form of a decimal, we like to convert it to a percent. So we multiply the efficiency times 100%, which is like multiplying by 1. It doesn't change anything. But it changes the decimal into a percent. Okay? And there's a reason for that, in case you're unaware. Percent is French. I'll write over here because it's not part of our... Percent is percent, which is out of 100. That's what it means. So this little sign just means out of 100. So if you write 100%, you're basically writing 100 out of 100. That's what you're doing. So let's say you take the number 0.9, right? And you multiply it by 100 out of 100. Well, it's going to turn into 90, isn't it? Over 100. Right? Multiply the tops, 90 over 100. So that's out of 100, so we just call it 90% instead of 0.9. Most people realize that these two things are exactly the same. It's two different ways of saying the same thing. And personally, I don't even use the percent very often. I just get an answer of 0.9. I know it's 90%, but textbooks like to put this part in, so we'll put it in too. So let's get rid of this so it doesn't get in our way. Okay, so let's look at an example. Let's say we did some work and we figured out that the AMA for some simple machine was 1.8. And then we did a bunch of more work and we figured out that the IMA was 2. Right? Well, then we can calculate the efficiency very simply by writing the AMA divided by the IMA, and we can multiply by 1. Or 100%, 100 out of 100, just to change the form. And so what we get is nice and simple. We get 1.8, I'll put efficiency here, 1.8 out of 2 times 100%, right? And that means that the efficiency is 0.9 times 100%, and that changes it to 90%. 90%, 90 out of 100. So what that means is that this simple machine will take 90% of your efforts and transfer them to the load. 90% of the efforts will be transferred to the load, right, to get something done. But 10%, so 90% of your effort is transferred directly to the load to move it. But 10% is wasted on friction or stresses and strains and so on. It's basically just wasted. We lose 10%. It's not a bad machine. 90% is pretty good. Some machines are less efficient. A machine that's only 20% efficient isn't very good at all. We might not even want to use it because it might require too much force. So we're looking for a machine that has the highest efficiency, which means that we waste less and we get the most of our effort transferred to the load. So that's how we do a simple way of doing the efficiency of a simple machine. The IMA divided by the AMA on top divided by the IMA below, and if you want, times 100%.